Hey engineers, and welcome to 1.2 part 3. In part 1, we talked about different ways energy and different sources of energy. They were inexhaustible, renewable, and non-renewable. And then we learned about the power grid and where our energy comes from, how it gets to us through those different means, and how this grid works. Today we're going to talk more specifically about electricity. And this is going to be a two-part series where I'm just going to give you an introduction. Those of you who have been through physics kind of already have this material right here. And if you're not through physics, you're going to get a leg up when you take physics to electricity. So we're going to talk about where electricity comes from, what is the difference between voltage and current and resistance. I think that's where we're going to end up today. So let's get started. Electricity. It's the movement of electrons. We knew about electricity before we knew about the electron as what caused it. And you'll see that actually makes an interesting problem when we get a little bit further here. But we knew about electricity, I think in like the ancient Egyptians, they had what are called voltaic piles. They would take salt water and they would separate them by leaves, and you could actually make a battery. They had batteries thousands of years ago. I don't know what they used them for or what, but we've known about electricity for quite a long time. At the atomic level, what is an electron? We drill down to what's called an atom. And atoms are comprised of protons, a nucleus here in the center. You've got the positively charged things. They're red. We call them protons. The neutrally charged things, we call them neutrons. And orbiting around the outside, we have what are called electrons. Now, an atomic number of something, so this looks like beryllium or boron if this is 4, because it goes hydrogen, helium, lithium, beryllium. The atomic number is just you count the number of neutrons that are inside of there. So 1, 2, 3, 4. Hydrogen, helium, lithium, beryllium. So beryllium, this is, according to the periodic table. Electrons, those are the negatively charged objects which are orbiting around the outside. Now, I don't know about you, but I think I remember asking my physics professor in college, like, okay, if this is negatively charged and that's positively charged, why don't these things just go straight to the center? Like, why when I see these pictures of these atoms, they're like orbiting around it like little planets? And this is not. This is just what we call a model. This isn't what really is happening, and this isn't really why. It breaks down at that level. These orbitals, they work good for certain things, but it's not truly what's happening inside of or outside of an atom. The valence electrons are in the outermost ring. We call those the valence. So an atom is always trying to fill up its outside ring, but again, that's really just a model. It's not truly what's going on. But it explains a lot of phenomenon that we view when we look at different elements. The Bohr model, this was the orbiting model, and then they have the electron cloud, and this is what we call quantum mechanics, if you've ever heard of that. There's a probability where the electron actually is or isn't, and where it pops into and out of existence. It gets pretty crazy. It's a mathematical way. The quantum world is very different than the world that you and I live in. You can do a little bit more digging on that if you'd like, but suffice to say that I know that I don't understand it, and I know that it gets really weird. But I don't need to understand it to be able to do my engineering. The periodic table, yeah. So, in these different orbitals, there are different numbers of electrons that can fit in the outermost valence band. So in the first orbit, there are 2. In the second orbit, there are 8. In the third orbit, there are 18. The fourth orbit, 32, 50, and 72. So just depending upon what element you have, that dictates how many it wants to get to fill up that outermost shell. So copper, for instance, and we all know that copper is a really good conductor of electricity, like all the copper wires in your house. Everything electronic that you have, the circuit board has been laid with copper. And so what makes copper such a good conductor is the fact that this outermost shell only has one electron. So it wants to get rid of that so that its outermost shell is then full. So copper is a really good donator of electrons. So this electron here is very easily given away. And so when you give an electron to the next thing, we call that electricity, the flowing of an electron. So sulfur, you can see here, sulfur, it's not real easy to give away 6. It would rather just take in 1 or 2 to fill up its outermost shell. So this is going to be a good insulator. So it would absorb an electron. It doesn't like to give electrons. Electricity at the atomic level. So what's going to happen here, here's copper again, and you're going to have an electron come in. It's going to knock free one of those electrons, and it's going to push it on down the line. You remember those Newton's cradles? These things right here? Do you remember? I don't know if you've ever seen these. This is kind of the way electricity works, that an electron comes in, goes to the next, and one on the other end pops out almost immediately. So electricity flows at roughly the speed of light, the speed of information, that one hits the next. It's not like one electron travels through the whole circuit. It's being knocked through, if you can think of it that way. And here's an electron flow. You have an electron coming in, it goes knocks right down the line, kind of like that Newton's cradle that you just saw, and that's what we call electricity. There's a few different things that we like to use. Conductors. Electrons flow very easily between the atoms. Some really good examples are copper, obviously. Gold is an even better conductor than copper, but gold's really expensive. But in some applications, we use gold because we need it to be that much better of a conductor. Believe it or not, platinum is an even better conductor than gold. So it starts getting more and more expensive. Some insulators, mica, glass, quartz, wood, plastic. I mean, plastic is the big one. That's what's going around all the wires in your house. And like, if you have some tools that you use for electricity, you want to insulate them so you don't get electrocuted yourself. In this picture right here, there's a bunch of conductors, like the inside of the wires, that's copper, and then this steel right here is a conductor. But then the cladding, or the insulation they call it, around the wire, there's a different insulation here, and these are all tied together with another insulator, and then the rubber around the handles, those are also insulators. A few electrical terms: voltage, current, and resistance. Voltage, the units for voltage we call volts. Like maybe you've heard of 120 volts or a 9-volt battery or a 12-volt battery. The abbreviation for voltage is the letter V. Current, that's how much electricity is, how many electrons are flowing per second. The units are amps, and that's abbreviated with the letter A. And then resistance. Resistance is the opposition to current flow. How easily electrons will flow through a conductor. The units that we use are called ohms, and it's the Greek letter. It's called omega. It's the last letter of the Greek alphabet. This is the capital letter, like the letter Z. The last letter of the English alphabet. The last letter of the Greek alphabet is omega, and it's this upside-down horseshoe-looking thing. And I want to talk to you just a little bit about what these things mean. So here I am. I'm over at a circuit simulator. This is called the PhET. It stands for, it's at the University of Colorado's website, phetcolorado.edu. And so every circuit needs to have 3 things. Thing number 1 is a voltage source. Now, this could be a battery, this could be the power station, this could be a photovoltaic, like a solar panel, but something that provides a voltage. The second thing that every circuit needs is a conductive pathway. In this case, it's wires. Maybe you've been electrocuted before and you are the conductive pathway. The third thing that every single circuit needs is what we call a load. L-O-A-D, a load. And a load can be a resistor, a load could be a light bulb, a load could be anything that dissipates current. So, for instance, if I have a battery, I'm going to turn this this light bulb. Then I hook it up, and now all of a sudden, yay, I have current flowing through here. The movement of electrons is called current. Now, going back to my circuit, if you're missing one, so here I have the voltage source, the conductive pathway, and if I don't have a load, this is called a short circuit. I'm short one of the three things. Maybe you've heard the term short circuit before. And a short circuit is exactly, you get a fire, you get smoke, you get all sorts of craziness. If you hook things up incorrectly, like let's say I have my light bulb, and you know how I'm supposed to hook it up here for this to work properly. But what if I hooked my light bulb up and I hook it up not to this connection, to this connection? I have a short circuit. Maybe I start hooking up wires and I hook wires up incorrectly. I hook this wire up to here and I hook it up to there. Boom. I have a short circuit. The current wants to travel the path of least resistance. So let's talk about what is voltage, what is current, and what is resistance. So voltage in the electrical world, I had a professor. I went to technical college after. I have a bachelor's degree. I went to technical college and I have an associate's degree in electronics, and I went to grad school and I have a master's in education. And in my technical degree, there was a professor who taught me the difference between voltage, current, resistance, and I loved it. It was beautiful. I'm like, Dr. Hoppy, I wish I would have had you 10 years ago, because I went all through high school, all through college, not really understanding what the difference between voltage, current, and resistance is. And he said that this is like water, and your voltage source is like pressure. If you increase the pressure, watch me increase the pressure. If I increase the pressure, I can push more water through the pipe. Just like a super soaker. The more you pump that squirt gun up, the faster it's going to shoot water. So voltage is like pressure. The harder you push, the more electricity flows. The less you push, the less electricity flows. Resistance. Resistance is like a kink in the pipe. If the harder you kink the pipe, the less electricity flows. So I'm going to kink this pipe more. More. I'm going to really kink the pipe hard. And you see how I slowed that down? The bigger the kink in the pipe, the less electricity flows. Let that kink go, more electricity flows. And that's the relationship between voltage, resistance, and current. And I have different things to measure how much current is flowing, so I can actually show you that if I increase the kink, more and more kink, I get less and less current. If I have my pressure, if I have more and more pressure, more and more current. Here's where I'm going to end us today. Just that idea, and this is called Ohm's law, that if you increase the pressure, you have more current. If you increase the resistance, you have less current. That idea, that's where we're going to leave today, and that's a huge, huge understanding. More pressure, more current. Less pressure, less current. Resistance. More resistance, less current. These are inversely related. Less resistance? Whoa, I can actually have so little resistance that I create a short circuit. And that's That happens in real life, actually. Maybe you've plugged in too many things at your house, and you've got these devices called a circuit. What's it called? A circuit breaker. Yeah, circuit breaker. And there's difference between circuit breakers, ground fault circuit interrupters (GFCI) and an arc fault circuit AFCI. So we'll talk about those in to come. But suffice to say that I'm just looking for the relationship between resistance, voltage, and current today.